The physics of banked curves is kind of neat. Here, I'll draw a picture and then I'll talk us through it. So this would be like a cross section. So we've somehow cut apart our curve. Let's say it's got an angle of X down here. Our car is driving around this curve. Let's say we're looking at sort of the back view of it. It's got four tires touching the road. I can see two of them. It's got a bumper, and it's kind of got a back window to a roof. So from the perspective of looking at this cross section of the incline, that's what I would see. The car is zooming around. Free body diagram wise, there's definitely gravity pulling this thing straight down. FG. And there is a normal force. By definition, the normal is always perpendicular to the surface. So I'm going to draw it here. Oops. Let's make that a bit neater. The normal force fits in there. The perpendicular would be, it's perpendicular to the surface. So there's a 90 degrees in there. There most likely would be friction on the car as well, but that depends on the scenario. If the car is going around the curve too slow, then there's a danger that the car would slide into the middle, kind of like an object on an incline that we saw before. And if it's going too slow, the friction would be uphill to keep it from falling into the middle. But if the car is going too fast, then the tendency would be the car is going to drift up and out of the curve. In that case, friction would be downhill to help it stick to the curve, to help it not slide up and away. Unless we know what sort of that threshold speed is, I don't know if it's going too fast or too slow. I don't know that condition. To figure out the condition, we're going to do this weird thing where we're going to consider a car going around a banked curve as if there was no friction. So this is going to be the threshold speed. Imagine the road was perfectly icy. You wouldn't even have to turn your wheel. You just sort of slide around the outside of the curve. What's cool about another thing that's cool about this is when a car is on a banked curve, it's actually accelerating horizontally. If it's not drifting up or down the bank, then the center of its curve would be somewhere, the way I've drawn it, to the right. Its acceleration would be pointed that way. So just like we did way back at the beginning of forces, when an object's accelerating, anything that's on a funny angle, we have to find components compared to that angle. Components of the force that's on an angle. So in this case, in a banked curve, the car is actually accelerating horizontally. So gravity is okay since it's already perpendicular to the horizontal. But I need to find the components of the normal force. On a banked curve, oops, let me redo that, that's a little bit big. On a banked curve, the normal force is doing two things. Part of the normal force, I'm going to call it Fn with a little v for vertical. Part of the normal force is fighting gravity. And another part of the normal force, I'm going to call it Fn with an h for horizontal. That's helping pull the car around the curve. Going to work through both components. If I start with the vertical, the car's going around the circle. It's not drifting up the hill. It's not falling down the hill. It's just sticking to the bank, going around the curve. So I could, like I've done before, say that the up force is equal to the down force. The up force is this thing that I've called Fn v for vertical. That's going to be equal to gravity, which is going to be mg. I need to do a little bit of trig work to figure out what Fn vertical is. If I look at the angle x, I'll switch to red. We got kind of a parallel line theorem going on, Z pattern. This angle here is the exact same x. If that's x, then this here is 90 minus x. If that's 90 minus x, between the red and the green is another 90, then this angle in here is x. So let me talk you through that again. We got a Z pattern. This angle between the dotted line and horizontal, that's an x. The dotted red line is perpendicular to the normal force, so there's a 90 minus x, the complementary angle. And then the red horizontal line and green Fn vertical, they're also perpendicular. So those two have to add to 90. That means the angle between the vertical component of normal and the black line normal is the same x. If I do a bit of trig, I know the hypotenuse is the normal force. I'm going to redraw it actually because I'm getting a little bit, I don't want to confuse things. This is Fn vertical. This is normal force. This is Fn horizontal. From our geometry, I figured out that that's the same angle x. So looking at this, Fn vertical, it's related by cosine. So SOHCAHTOA, opposite over adjacent, so adjacent Fn over the hypotenuse, Fn vertical over Fn is a cosine thing. So Fn all by itself, or actually let's go Fn vertical. Fn vertical is Fn multiplied by the cosine of x. We'll need that a little bit later. Now plugging into, let's jump to the horizontal. It's going in a horizontal circle, so that's an F net equals MA thing. The only force pulling it sideways is Fn horizontal. Since it's going in a circle, that's equal to mv squared over r. If I go back to my triangle, now I'm curious about Fn horizontal. It's going to be a sine relationship because it's opposite the angle. Fn horizontal divided by hypotenuse of Fn is sine x. So Fn horizontal is Fn sine x. This is the way I came up to find this little equation. You might see a different way to get to the same endpoint, just doing trig in a different order. But I'm getting here that, I'm getting that Fn sine of x equals mv squared over r. Almost done. Fn vertical, I've got two equations for Fn vertical. This one that I did in green is equal to gravity, which is mg. So let's put our number 1 by that one. And Fn vertical, this one I did in purple, is equal to Fn cos x. If I combine those two, I can say that mg is equal to Fn cos x. Or what I'm going to need to clean up the horizontal, Fn is mg over cos x. That one's kind of cool, that equation I just numbered 3. Really what that's saying is your normal force is the boring case mg divided by the cosine of x. Cosine of x is always less than 1, so your normal force is going to be bigger than mg. When you're on a banked curve, you actually feel heavier than your regular weight. All right, almost done. Fn is the same as mg over cos x. And if we take that and multiply by the sine of x, that's equal to mv squared over r. M's are going to cancel. I'm going to rearrange for v squared. I get r, because I'm going to multiply it out. I've got a g. And sine x divided by cosine x, grade 11 trig identities, that's the same as tan x. This equation will give me the threshold velocity for a car to make it around a curve if there was no friction. So when given a banked curve question, we're always going to start with this. V squared equals rg tan x. Calculate how fast a car could go around a curve. Then depending how the question asks, if it gives you a speed, use the given speed to compare to this calculated speed. If the given speed is faster than what v squared equals rg tan x says, if a car is going faster than that, then the friction has to be downhill to help the car make the curve. Or if the car is going slower than what this calculates out to, then it's going too slow and friction would be uphill. We usually in grade 12 won't push you to do anything with the friction, just identify which direction the friction is. If there were friction, we'd have to take components of the friction. It just adds to the math. It's not impossible, just a pretty big question. But for now, you should be able to follow this proof. I was a little bit disorganized, but hopefully it made sense. We get this new equation, v squared equals rg tan x. That's what we'll use to figure out that sort of threshold speed.